Hello everyone. In this video, we are going to discuss two of the very important topics, which are multivariate linear regression and feature scaling. So basically, these two topics does not involve any mathematical formulas or geometric interpretation. So these are comparatively very easier topic to understand, but they are really very important topics to understand in machine learning. So far, we have already discussed in day 1, 2, and 3, we have discussed linear regression in single variable. So now we're going to start off with the multiple variables in linear regression, right? So the very first thing that I'm going to show you is what exactly is the meaning of multivariate. So multivariate basically means that you have multiple features. So I'm going to write here multiple features. So what exactly is a feature? So now I'm going to take our very old example of housing prices, where we have seen that we have prices as the output and we have area as the input, which was our x. So we were having the prices, and we were also having the area in square feet. So we can take some values of prices and areas in it, right? So I'm not going to write the values because we are not going to take a look at the values. So in the linear regression tutorial, I showed you that price is actually the output and area is the input, right? So if you input area, you get the output as the price. So when we were drawing the graph corresponding to this data set, what we were doing is we were plotting area here and price here. Now the reason why we were writing area on the x-axis instead of y-axis is because area is independent variable. So it means that area does not depend on price, right? So if you have a house, let's say it is 500 square feet in area, it does not matter what the price is, the area will remain 500, but price is a dependent variable, so it depends on the values of area. So if I say that price is, let's say, $1,000 for 500 square feet area, then this price is dependent on the area. So area is known as independent variables. So we have another name for area, we can call it as independent variables. So output is a dependent variable. Now all the independent variables in our data set are known as features. They are known as features because they are actually featuring the outputs of our data set. So now in the previous tutorial where we were discussing linear regression in one variable or in a single variable, when we were discussing linear regression in single variable, we were only having one feature, which was area. So this was the only feature, x, we were calling it x, and this was y, and we were using I to represent a particular record or a training example like this. And let's say we have n training records. So we have discussed what will be the hypothesis in case of single variable, which is a single feature. We have also discussed the cost function and the gradient descent in that case. Now we're going to see what will happen if you have multiple variables. So let's say I have one more independent variable, which is, let's say, number of floors. So let's say we have 4 floors here, then 2, then 3, and so on. So now the output, which is the price, it now depends on area as well as the number of floors. So in this case, we have multiple variables or multiple features. So that's why we call it as multivariate linear regression, right? So now we are going to see what will be our hypothesis function, what will be our hypothesis function in case of linear regression in multiple features, right? So we have studied hx in case of single variable, hx was equal to theta 0 x plus theta 1 in case of single variable. So think about it, what should be the hypothesis function in case of multiple features? So in case of multiple features, we have hypothesis as theta 0 x 0 plus theta 1 x 1 plus theta 2 x 2, and it goes on till theta n x n, where n is our number of training examples, sorry, number of features, where n is the number of features. So now we have got our hypothesis function in case of linear regression in multiple variables. Now if you try to there is one more fancier way to reduce this whole term, this whole big term. Let's say this is equation 1. You can actually reduce it in this form, which is theta transpose x. So this can be reduced to this, where theta is nothing but a matrix, of the form theta 0, theta 1, and goes on like theta n, and where x denotes x1, x2 till xn. So we have theta, we have x. So now why we have done the transpose of theta? You can see this t represents here the transpose. The reason is that we want to, in order to obtain this, we will have to multiply theta and x. So according to the rules of matrix multiplication, you cannot directly multiply this like this. So you will have to take the transpose. So theta transpose will become theta 0, theta 1, and goes on theta n. And if you multiply this by x, now it will be like this, x1, x2 goes on like this. So now it's possible to multiply this by this. Now matrix multiplication is possible here. Theta 1 will get multiplied to this. Also we have x0 here. So we will be able to obtain all these terms using this type of matrix multiplication. So in case of multivariate linear regression, we have this hypothesis function. Now we are going to discuss cost function in case of multiple features. Now see, the cost function and gradient descent, the algorithms, the formulas will remain same. What changes is the hypothesis function, because hypothesis function is actually the curve that will represent or that will be used for prediction. So in case of multiple variables, the hypothesis changes, and accordingly in case of cost function, which was j of theta 0 comma theta 1, and since we have n parameters, I write it like this. Now this will be equal to 1 upon 2m. Again sigma goes from I equals 1 till m, and then we were having h theta x minus y I, and this was xi whole square. So this was our cost function, a general cost function. And you can actually put, if you will put hx from this equation, which is, let's say this is equation A, then you will get cost function for single variable. And if you will put x hx theta transpose x inside this cost function, you will be able to obtain the cost function. So simple, right? We are just going to make some tweaks and we will be obtaining the cost function. Now the last thing is the gradient descent. And we know that gradient descent is basically used to find out the minimum cost, right? So we just try to do the take some alpha learning steps, and then we try to reach the minimum value by taking the slopes. So in case of gradient descent, the algorithm was, if you remember, it was repeat until convergence, and inside this we were having theta j, or let me write theta 0, and we were using this symbol. We also explained the use of the symbol will be theta 0 minus alpha times, which is the learning rate. Then we are going to calculate the partial differentiation with respect to theta j, or theta 0 in the first case. And inside this we will have our cost function, which is this one. And we know on simplifying, when we try to differentiate it, so I'm just going to write here, it will be like this till theta n. So if you will try to reduce this term, you can take the partial derivative, which will cancel this 2 here. And if you remember, the result was, so if you will solve that, the result that you will obtain is 1 upon m, 2 will get cut, and then we have sigma goes from I equals to 1 till m h theta of xi minus yi dot x 0, and here I'm going to write I. So this was, we have already seen how we have just calculated the differential, the partial differentiation of this with respect to theta 0. So we will get something like this. Now this thing here is new. Now this is x 0, and you can see I here. What this represents is, it has a subscript. This subscript is basically representing the feature index. So this means we have x0. Let's say that the number of floors is x0 and input is x1. So x0 represents the feature index, which is floors, and the I represent the ith training example. So if I is equals to 2, then we are actually trying to get this value. So this will be the value of x02, right? So we will multiply it here. Now similarly, we also have the same formula for theta 1, because in gradient descent we try to update, or simultaneous updation. So we try to do the simultaneous updation of all the parameters, all the theta parameters, and the formula will be the same. We're just going to write h theta. Now I is the training example. So instead of writing it in the subscript, we should write it in the superscript. So y should be written like this, right? So xi, we should write it like this, minus yi dot. Now we are trying to get to the x1 function. x1 feature and ith training example. And similarly, we can construct it like till theta n, and we can obtain the gradient descent algorithm, and it will repeat until convergence. That's all we know. So that's all in the multiple or the multivariate linear regression. We don't need to actually do anything, just we will have done some tweaking inside the hypothesis function, and we have just put it inside the cost function and the gradient descent. So now we are going to head towards our next topic, which is the feature scaling. Now see, feature scaling is not a prediction algorithm, and it is not even any modeling technique, and we're not the feature scaling is actually a method, right? A method, or I should say a technique, right? So it is a method or a technique. So let's see what is the idea behind. So let's first see the idea behind feature scaling. So the idea behind feature scaling, or the objective of feature scaling, is to speed up gradient descent. The idea is to speed up gradient descent. So what is the meaning of speeding up the gradient descent, right? So if I say that I have a graph something like this, and we have a curve here, and here we are getting the minimum value. So our theta parameters are going to continuously update to the next, to get to the next point, and it will do that again and again. So it will obviously take some time for the gradient descent algorithm to reach to the minimum position. Now we will have to find some way to speed up gradient descent. So feature scaling is one of the method or technique to speed up gradient descent. So we already know what exactly a feature is, and scaling means we are going to just reduce the range of the features. We're going to take a look at that, right? So the idea is to speed up gradient descent. We will see how this technique will speed up that. So how can we speed up the gradient descent? Is by having each of our input values in roughly the same range. By having each of our input, and remember input is nothing but our feature, so each of our input in same range. So what does this mean? So here I'm going to take an example to explain you this. Now let's suppose I have a data set, and in this data set I have two features. Now this is actually the price, and this is the area, let's say. So now in area we have, let's say, four. I'm going to take four examples. First we have, let's say, 10, then 1000, then 3400 square feet, and 500 square feet, and let's take one more, which is let's say 7000 square feet. Now if your data set has features and the range of the feature, and someone says what is the range of input, so the range of input in our case is from 10 to 7000. So this range of our input is very high. It's very high. You can see there are so many numbers in between. So that's why this range is very high. So in case when we have, so there is an observation, it is observed that gradient descent algorithm, this algorithm performs slowly if range of the inputs, if range of the inputs is high. So if the range of the input is very high, then it does not matter what algorithm you're using. The gradient descent will, it is an observation that it will reach to the minimum position in a very long time. It will take a very long time to do that. So that's why we are introducing feature scaling, because what it is going to do is it is going to reduce this range. It is going to make this range shorter by using some mathematical formula, and then it will speed up gradient descent. So let's see. So let's now just I'm going to try to define what is feature scaling. So basically feature scaling is a method used to normalize range of the inputs, and instead of inputs I'm going to be more specific by writing independent variables. So feature scaling is a method used to normalize means we are going to reduce this range to some very smaller range, and why we are doing this is because it will speed up the gradient descent, and that's our observation is. So we can also say variables or features of our data. So that's what is the definition of feature scaling. We normalize the range. Now this technique is basically known as data pre-processing. Now if you have a machine learning algorithm, if you want to perform prediction on the data set, you cannot use any data set, right? You will have to pre-process the data set in such a form that if you try to implement machine learning on the data set, it should perform well. The performance should be good. So you can see in this data set we have a range which is very high, and this will actually become an hindrance in slowing down the gradient descent, and that's why we are going to perform feature scaling. We are going to reduce the range. All right, so now let's see how to reduce the range, how to reduce this range. So it is generally an observation that a range between, so if I have x as the independent variable, so if it is between -1 and 1 or minus 0.5 and 0.5, now if you will try to make your features in this range from -1 to 1 or from minus 0.5 to 0.5, it is an observation that gradient descent algorithm performs faster. It will perform faster. You can see here x, the range of x is from 10 to 7,000, so much high. So let's see our very first technique to normalize this range 10 to 7,000. So the first technique is very simple. In this technique, what we do is we pick up the maximum element of the range. You can see the maximum element of our range is 7,000, and we will divide each term or each of the training example by this value. So we will divide 10 divided by 7,000, then we have 1000 here, so we are going to divide it by 7,000 and so on. So 7,000 will be divided by 7,000. So in this way you can see I have scaled the feature from 10 to 7,000 scale to scale of less than 1. Now you can see the value of x, if I will divide it by 7,000, it will be less than 1, because 7,000 by 7,000 will give me maximum of 1, else every value will be lesser than 1. So now if I will be having a data set like this, and what is the first task to do is to find out if the area or the features inside our data set is scaled or not. If the range is very high, we will pick up the maximum element and divide it with each value, and we will obtain a range which is a lower range, and then we will apply our machine learning hypothesis and then cost function, and then gradient descent will perform faster. So this is the very first technique. And then the second technique is popularly known as mean normalization. Now it is known as mean normalization. Now in this technique also we are going to scale this range to some smaller value. So the formula to, now what we are going to do is we will have to update the xi's, right? We have to update xi. So again I'm going to use this function. We are going to do the simultaneous update of all the training examples, and I represent the ith training example. So mean normalization says that what you have to do is just subtract xi with ui and s. Now what is mu I? Now mu is known as mean or average. Mu is known as mean or average. So if you will take out the mean or average of the feature x or xi, if you have multiple features, then you can calculate the mean by adding them up and dividing by the number of training examples. You can take out the mean, and then what you have to do is you will have to subtract that mean from each of these values. From each of these training examples, you will have to subtract the mean. So after subtracting, you will have to divide it by s. S is equals to maximum minus minimum, right? Maximum minus minimum. So what is the maximum value? Maximum value is 7,000. What is the minimum value? It is 10. So what we will get is 6990. So then we are going to divide each of this term by 6990, and we are going to do it like this. Now this is known as mean normalization, and this is how we actually try to scale our feature. A very good technique to improve the performance of gradient descent algorithm. Now in the next day, which is day 5, so tomorrow we will discuss, on 11th April, we will discuss logistic regression. We are going to start with the logistic regression, which is a very important topic. We're going to see the hypothesis function and cost function and everything in this case, which is logistic regression. So that's all for this tutorial. If you have any doubts, you can ask it in the live chat, or you can ask it in the comments below this video. I will take your doubts and I will answer them as much as I can. So if you have liked this video, make sure to subscribe our channel and hit the notification bell icon so that you will be getting all the notifications from our channel. So thanks for watching.